So we are looking today at combinations. So last week we were learning about permutations. So arranging group of objects in all the different orders that are possible. Given a group, maybe choosing 3 to arrange, so n of them. And now we're looking at combinations. Combinations are actually a little easier. Okay? When you're dealing with combinations, you are figuring out how many groups of items you can choose. C starts with C, which is helpful. Choose given a large group or a large group of people or objects or whatever it is. So combination is a selection of all or some of the members of a set without regard to order. If it's all, then the number of possibilities is going to be 1. So really, it's always going to be some of the members of a set. So we're going to look at sort of a long way of doing this one. So it says 4 students all have put their names on a piece of paper for a draw. The first name drawn wins a $5 gift card for a local coffee shop. Second name wins a movie pass for Cheap Tuesdays. Anyone know about Cheap Tuesdays? It used to be. Tuesdays, movies were cheaper. So $2 Tuesdays when I was learning, but they don't have $2 Tuesdays.
No, now it's like $2.
Now it's $20 Tuesdays. In any case, second name drawn wins a movie pass for Cheap Tuesdays at the theater. Third prize wins an app they want for their smartphone. So again, you have to pay for those apps, so it's a bit of a prize. Number of different ways the 4 students can win the prizes is given by, well, we have 4 students, and we're going to arrange 3 prizes. Okay? So 4P3 is, what is it? 24. Same as 454. Happens to be because you're arranging 3, right? So 4 times 3 times 2. Same as 454. Right? Here are all the sample spaces. Okay? We started them for you. So you could have, so A is for Alex, B is for Banji, C is for Carol, D is for Janine. Then part of the sample space is shown and you're going to finish it. So this would be, for example, A winning the gift card, coffee shop app. Gift card, coffee shop app. So now the people are switched around, right? So order matters because they are different prizes. If they were all the same prize, the order wouldn't matter, but they're different prizes. Okay? So that's if A, B, and C are winning something. We listed them for you. If A, C, and D are winning something, then it could be A, C, D, A, D, C. It could be D, A, C, D, C, A. It could be C, A, D, or C, D, A.
Maybe it was something explicit here.
Then with these 3 people winning, ECD, EDC, sorry, DBC, DCB, CBD, CBD. Okay, and then if these people, 3 people win, could be DAB, DBA, DDA, DAD, or
question is, the one thing with permutation combinations and this stuff, you can't actually determine like what all of them necessarily are. It's going to come in.
Okay, so this shows a reasonable number of people, 3 prizes. We listed all the possible ways, way to win each of those prizes. So then it says, supposing that instead of the 3 different prizes, they're all exactly the same. So would the group ABC be any different from the group ACB or BCA? So what would happen in here? If all the prizes were the same, do we need all of these? No. There's only one grouping, right? Because they're all winning the same prize. So we don't take all of these. So then we would have this grouping, and this grouping. Okay? So in this case, there's only 4 possible groups of 3. Okay? So, no. Because prizes are the same. So the order doesn't matter. Okay. So the sample space reduces from 24 groups down to 4 groups. Any ordering of 3 people is no longer relevant when the prizes are all the same. And how many ways are there of ordering 3 people? In factorial ways, which is 6. So we have 24, and now we're going to divide out by 3 factorial, because we're eliminating all of those that are going to have the same result. Okay? So 24 divided by 3 factorial gives you 4. If the draw was expanded to include 10 students, but still with exactly 3 exactly the same prizes, then how many different groups of 3 people could win the prizes? So we could then have 10 factorial would be if the prizes, 10 factorial divided by 7 factorial would be if the prizes were all different. Okay, so this is the same as 10 3, right? So this would be for different prizes. Okay. Now, based on this, we had to divide by 3 factorial the arrangements of each in that group, right? So now we're going to do the same here. So we would take 10p3 divided by 3 factorial, the same as 10 factorial, 7 factorial. I'll do it in green so you can see it. Divided by 3 factorial, which just goes in the denominator. And simplify the fraction. So let's do that in our head. That would be 10 times 9 times 8 over 3 times 2. Right? This divides into the 7 factorial up there. 2 goes into that 4 times, 3 goes into that 3 times. So that's 120. Don't need a calculator. So that's choosing group. So what's nice about this notation that we're going to get to is that it has a C. So it's a combination. But when you say it, you kind of think of having that 10 people. And we're going to choose from that group, groups of 3. As opposed to arranging them. We kind of use arranging for permutations, but it is different for people. You can say the permutations of, but when you actually think of doing it physically yourself, you're kind of finding these things. So what's nice about combinations is that the letters match up. Okay, so here, this is where we're going to come up with the formula. So groups of objects, where the order in which the objects were selected for the group is not important, are called combinations. The number of combinations of n objects taken r at a time, or the number of ways to select r objects, or choose.
Oh, that's where the are.
Yep.
Oh.
Then can be determined. So we had this before, the last question. I took this, okay? So I had 10p3, and I divided by 3 factorial. That's how many in our group, and that was my factorial. So those that r is going to match up. So this is going to be divided by r factorial. So this is your formula for NPR. We're dividing that by r factorial. When you divide by r factorial, it's going to, and simplify the fraction, you're going to get both this and this in the denominator. That's fraction rules. Fractions in half. Okay? So, here's the notation. This is what's in calculator notation, and then there's this notation as well, and IB uses both. Alberta Ed for 30-2 uses both, but I don't know if for 30-1, oh yeah, it is on there too. Oh, it doesn't matter. Just be careful, that is not a fraction. So some people will go like this. Okay? That's a fraction. This means n choose r, so it's made up of factorials. Okay? So n choose r, or NCR, is n factorial over n minus r factorial, r factorial. Doesn't matter what order that denominator is. That's the order that the formula sheet has. But you can put r factorial first. Okay. It's located same place as NPR in your calculator, one line below. So, one line below. So math, probability, number 3. Okay, so if we do 10, choose 3, get 120.
So this is what this is. I thought it was way more complicated.
Okay, so these two numbers down here add up to n, right? N minus r, you just take those two numbers, not with the factorial obviously, but those two numbers, n minus r and r, you get n. That's how you get them, right? So your permutation NPR was n factorial over n minus r. And now we have the r factorial here. Okay, so if you didn't have a calculator, okay, now we're going to practice. So, 5 people are chosen from 8 male and 6 female applicants to represent the school at a climate conference. Determine the number of different groups that can be selected. So, different groups, okay? You just care about the group. You don't care about what order they're chosen, or what order they stand in, or they don't have a position in the community, right? If they had to be president, vice president, and treasurer, if you did something like that the other day, then that's an arrangement. This isn't. It's just groups of people going.
Okay, when I read the name of her, I was like, oh, that's interesting. And then I read the next one, I was like, oh, you did that intentionally.
Yeah?
Star Trek reference.
Oh, I did it. I don't watch Star Trek, so 14 people, okay, you're choosing groups of 5, so 14C5, that's it. it out in your calculator, but I'm just going to leave it like that. Okay. Then there are some restrictions on the next one. There must be 2 men and 3 women. In this case, there has to be 2 men. So now you have to look at that information. There's 8 males, and you have to choose 2 of them. So 8 choose 2 gives you the groupings of 2 males. For each of those groupings of 2 males, you have to have the women join them, right? So you're going to multiply. You're not adding together. It's kind of like that pathways when you have the rectangles that join at a corner. So each of the number of pathways to get to the corner, you multiply by the other ones. So each of these groupings, and then there's 6, and we're choosing 3. And again, you can figure out that value on your own. Notice how here, these add up, 2 and 3 add up to 5, the number of people in your group. And that's really going to be the case, unless you're choosing 1 out of 1 person, for example, and you don't bother showing that because it's just 1, then that's not going to be a great way to check. But in this case, you've shown all your work there. Only women, so that's going to be 6, and you're choosing 5 from it. That one. Only men, 8. 8. Try to make your N and R smaller than your C or your P. So writing this is not good notation.
So if you struggle with that, can you just use the other?
You could, yeah. For C, there isn't an equivalent for P. But yeah, for C.
Well, you have to make sense. One kind of one. Unless you're I don't know.
Okay, so now there must be at least 3 men in the group, at least. So there could be 3 men, there could be 4 men, there could be 5 men. This is where we're going to add those together. Because the first, if it's at least, so we start out with our group of 14, okay? And we're going to find the number of groupings that have exactly 3 men. Say it's 7. Then we're going to figure out how many groupings with 4 men. Say it's 10 of them. On the total now, we add those 2 together. So we're going to add in this case.
So maybe you could just be like you just choose 3 men and then the rest of it doesn't matter. Like you're, I think it's like 8 choose 3 and then times 11 choose 2. Doesn't matter what the rest of them is. Doesn't matter if it's 3.
No, that might get you might count more than when you do that. You're going to have, I don't know.
We'll see.
There's some ways that you can't do that, but I have to think about how to explain it. You can compare. But here, so 3 men we have, what do we have from written here? We have 8. So this is going to be 8 choose 3. Within that, we then have 6 choose 2. We have to round out that group, okay, with the women. Plus, then for 4 men, we have 8 choose 4, and then 6 choose 1. And then for 5, we have 8 choose 5. Okay, so we'll find the value and then we'll compare to what you're using. So, some of these you can probably do in your head. So 6 choose 4, 6 times 5, roughly 3 times 5 is 15. Oh, calculator, I would just go copy the last one, go back and change the 3 to a 4, and then 15 change that to a 6. Yeah, this is why overlap.
Oh, you're not concerned with I think that.
Okay, so 56 plus 420 plus, oh, look,
You were all just like,
okay, so next one, there must be at least one woman in the group. So think about it. Same way that we did last one, we can kind of change it. We have to go, okay, that's when we have exactly one woman, or exactly 2, or exactly 3, or exactly 4, or exactly 5. And we have to add those all together. A little bit faster is to think about the complement. We talked about that before. The complement is the total number of ways of grouping them, 5 people, and taking away the complement of this, which would be 0 women. So this would be total minus 0, which is the same as all men, right? And we already have total is 14C5. Only men is 8C. That's right. 0 women is only men, so that's 8C5. So let's actually find this one. If you wanted to spend the time doing 1 with 2 with 3, etc., to get the same answer. Okay, next one. Vera, one of the female applicants, must be in the group. So there's one of her and we're choosing her. So again, you have to show that? Not really. Okay. Then we choose, it doesn't say anything else about how many males and females, so just that person has to be there. So she is chosen. Then we have 13 people left to choose the remaining 4 spots. Okay, so then next one, Herc and Spock. Well, yeah, sorry. I did it. I mean, I know enough about stuff.
so they would all be together. Economically, that's fine.
Yeah.
So I thought we were getting there. Anyway.
Okay, so Herc and Spock, 2 of the male applicants, cannot both be in the group. So they could, neither of them could be in the group. One of them could, or the other, but not both. So this is another example where I would use the complement. Okay? Because otherwise you'll have to do neither of them in it, Spock in it only, Herc in it only, and then you figure out how to do these together. Might be easier to go total minus both total we know is 14 C5. Both in it. You can go 2, choose 2, or 1, choose 1, plus 1, choose 1, or not even show it, because that value is 1. We know that we have to have them in there. You might do that just because they're going to be together. Okay, and so again, no other restrictions. We don't care how many males or females and the rest of it. But we've taken these 2 out of the 14, so we're left with 12 to choose the remaining 3. So let's do this one. I already have in my calculator 14C5. I'm not going to bother putting this in because that has a value of 1. So I'm going to go here and put in 12 and 3. For each group that has both Kirk and Spock, there's this many ways of choosing the remaining 3 people. This is really just a value of 1, right? Okay, next common type of question, although currently they will not put a question on the Dakota exam about a deck of cards, apparently. Because some people have never played with a deck of cards. Not that you have to, because they'll give you information about the cards. But in any case, let me see if I have a deck of cards here.
Never seen that cards in your life before, and no, never seen a different card. Never even played. I don't even know. Yeah.
If you've never seen a deck of cards, you gotta learn.
Yeah, I have seen my uncle play.
I used to have
Why? Want to do magic?
Okay. So, you're putting in a casino. Nice. Okay, so, deck of cards. How many, so who knows how many cards are in a deck? A regular deck. A regular deck. Minus jokers. No open jokers. 52. Okay? How many suits? 4. So, 52 divided by 4 is what? 13. So there's 13 different cards in each suit. Okay, so and they go, depending if you consider ace to be high or low, consider it to be a 1. So ace, 2, 3, 4, 5, 6, 7, 8, 9, 10, jack, queen, king. 13 cards. Okay? And 13 cards for suits. What else do we? Face cards are jacks, queens, and kings because they have faces on them. They have a king, or a queen, or a jack. Okay? And aces have one symbol on it, and that they have an ace for ace. Okay? So, we might on a test put a question on this, because we explained what a deck of cards is. You don't have to know how to play a game or anything.
For this one, you do.
Well,
If I ask you with full houses, how many here know?
well, yeah, a few of you will know I didn't know what it was either. So
We need to
we'll
like
tell
have
you
a
what
class
it
where
is.
you play poker.
Not play poker.
I'm not even sure that's allowed. Actually.
Okay.
I got.
Okay. Let's go with it.
Really?
All right. So for those of you that play poker, you can extend this to probability and realize when you're going to lose a lot of money. In any case, a standard deck of cards consists of 4 suits. We just went through this: clubs, spades, hearts, and diamonds. And just another thing I forgot to say. These are red. Oh, these are red, and these are black. Okay. Each suit consists of 13 cards, 9 numbered, 3 spades, and 1 ace. Determine the number of different 5-card poker hands that can be drawn from a deck of cards. If in each hand there are exactly 3 red cards. So think about it. If you've ever played cards before, you might put them in order as you get your cards, but order doesn't matter. Your hand, your 5 cards, you have them. They're yours. Or do whatever. So order doesn't matter. That's why this is a combination question. So, how many red cards? If there's 2 full suits, that's half the deck. Half of 52 is 26. Okay, that gets you all the combinations of 3 red cards. That's only 3. Your hand has to have 5. So now, the remaining cards are black. There's 26, and we're choosing 2 of them. Again, you're not going to find the actual numerical value. You can do that on your own.
Oh, I see why you couldn't do the other thing, because in the other one with 3 men in the group, you would have to be like, because I'm counting the groups twice, because here I'm saying like, here's the one man with this many not men, instead of just saying like, this many men. I'm double counting the ones where you can have a man and a man here.
Right. Yeah.
You know what I'm talking about. Everyone else is like, because I didn't explain that very well. My bad.
Okay, all black cards, 26 black, the 5-card hand. Okay, yeah, basic rules. All face cards. So remember, I said Jack, Queen, King for each suit. So there's 4 suits times 3 is 12 face cards, and we're choosing 5. Larry, what's up? No, it says exactly 3 red cards. Yeah, I did.
Yeah,
So this is the red, just check. This is the red, right? We have 26, and we're choosing 3 of them. You don't want any more red anymore. So this is 26 for red. Oh, this is 26 for black, right? So really to get this, it's 52 minus this 26. The different 26. Okay, so at least 1 king, so that's, you do it the long way, you do it the short way. So at least 1 king will be 1 king, 2, 3, 4. Okay, that's 4 calculations, right? That's the king. So you can go total minus no kings. Okay, so total is 52 choose 5. No kings means you could actually put 4 to 0, right? 4 kings and you're choosing 0 of them if you wanted to, but this has a value of 1. Okay? So no kings means you're going to then choose from all the non-kings. 52 cards minus 4 kings is 48 non-kings, and you're choosing 5. So if you want to show this, you can, but you don't have to. This is what you need. You've got to make sure this number doesn't include possible keys, right? What's Rita?
There's like this example, right? They say there's 5 cards that is the same.
Yep.
Like every term, the second number has to have the 5.
If you show every part of it, yes. But if it's, for example, yeah, so those add up to 5. It would be like, say I said you had to have 1 king exactly. So that would be, oh no, let's say something different. 1 king of spades. Then there is 1 king of spades and you're choosing it, right? And then you would have 51 to choose the remaining 4 cards. That would add up, but whether you show this or not, depends. So if you show every part of it, yes, those will add up to the number of cards in your hand. Okay, so 2 pairs. So think about 2 pairs. If let's say one of the pairs is a pair of 4s. Okay, then your other pair cannot be a pair of 4s because that's considered 4 of a kind, right? So your 2 pairs have to be different numbers. So of the 13 different numbers, you have to have 2 different numbers that you are having pairs of. So this is a little bit different. You have, it doesn't matter what order you put it in, but you can say, okay, 13 choose 2 will give you which numbers are pairs. So whether it's a pair of 10s, a pair of 2s, a pair of jacks, a pair of 3s, or whatever. And then within each pair, there's 4 of a kind in the deck. You've got to choose 2 for your first pair. The other pair, 4 choose 2. Okay? So this is 1 pair, this is the other. You need this so that you get all the possible pairs of pairs, right? So whether it's a pair of 10s and a pair of 2s, a pair of aces and a pair of kings. So this gets you all of those combinations. Have I got all the cards in the hand yet? 2 pairs is how many cards in your hand? That's 4. I need 1 more card. How many cards do I have to choose from for that last one? Can I use any of these?
No.
Because if I did, that would be 3 of a kind. Can't use any of these. So I have to go 52 minus 4 minus 4 is, what is that? 6 is 44. Choose 1. So that's harder. Take a little bit of thinking to get through that one. Really, what the thinking is this. Okay. 4 aces. That's often considered like the
Because
best
if
hands,
you
right?
have races, that means you only have full house. Or sorry, not flush, flush. But someone can still get you a straight flush.
Okay. In any case, 4 aces here. There's only 4 in the deck, and you're going to choose all 4 of them. So again, really that has a value of 1. Okay, that fills up your hand with 4 cards. Then you only have 48 to choose the remaining 1 card.
I have a question about
Yep.
So like the first step, right? There's 13 cards and you're taking like 2 different ones.
Yep.
And the next step you're trying to find like the same one, right? And like the next step you're finding like 30 cards to So what do you use to know if you have 3 options? The cards to go in the love option?
Only No, the 13 choose 2 doesn't choose a card. It just tells you what number the card's going to be. Is it going to be a pair of 10s and 2s? Is it going to be a pair of jacks and so it's not actually taking those cards out. So this is just saying that 13 choose 2 is giving you the number of saying, okay, you're going to have jacks and 2s, or you're going to have kings and aces. You're going to have 3s and 4s. So the 13 choose 2 tells you how many groups like that you have. And then of that, there's 4 jacks that you have to choose 2 from. 4 2s that you have to choose 2 from. Because remember, these have suits, right? So then there's 4 choose 2 ways of getting each of those. So it's not too, so this is where you can't just add up those R values, right? Okay, so let's finish off this group. 4 of a kind. So this was 4 aces. Okay. So 4 of a kind is kind of similar to this, but what's the difference going to be? That's 1. That's aces. That's 1 type of card.
You got 13.
13 different of these. So it's basically this times 13. So this is 4 aces. It would be the same if it was for 4 2s. It would be the same for 4 3s. So we keep adding those together. So it's the same as 13 times that.
So it's a similar idea to like what we did for the pairs.
So you can go 13 choose 1 if you want, or 13s. And 28. So, full house, you may not know. It is a pair and a triple. 3 of a kind. Okay? Maybe I'll just 3 of a kind. That's more. Okay? So, kind of similar to the last one. Let's do like the pair and the 3 of a kind. So a pair, that's 4 choose 2, right? For whatever number it is. 3 of a kind would be 4 choose 3, for whatever. Do we need any more cards than that? That fills up your hand. Now, is there a difference? If I did 13C2, that's saying, let's say it's Jack and 2 is one that one of those here. If this is Jacks and this is 2s, is that different from this being 2s and this being Jacks? Yes. Okay. So because they're not equal, right? Then really, if you change this to P, then order matters. So the order that you choose those 2 numbers matters because this is different from this. And that will take care of the corner.
Yep. The way I had it was 13 choose so that, but kept that as a C, and then at the end multiplied by 2 to get the possibility.
Yeah, you can multiply by 2. Yeah.
Okay. Right, because that's what you're getting rid of when you have this.
Yeah. Okay. So think about that a little bit. We'll stop there. But listen to this just before we do that. If you were gambling here, which no, you're not supposed to gamble, but if you were, and let's say you wanted to find the probability, if you are putting money down, what would you do to get the probability of getting 4 aces? Do that. Yes, so you would take, so the probability, for example, here of 4 aces actually 48C1 over, which is, that's actually, if you do that in my head, that's 48. Over 52C5. Let's just do that quickly.
But
48 divided by.
That because if you're trying to figure what your opponent could have, then you know they don't have any cards that you have. Or any cards that
We're just doing in general. Okay, 1.85 times 10 to the negative 5. Right? So, not great. Here's the last probability you want to think about, because I got a lottery ticket on the weekend. Why does a math teacher buy a lottery ticket? Not so sure, except anything that's not zero is not zero. There's a slight probability. But for a lot of maths, well, let's do 649 because a lot of maths actually changed. So 649 ticket, you hear that ad on TV. That means you have 49 numbers and you're choosing 6 of them. Order doesn't matter. Okay? So you will need to get one. So you need 6 numbers. So you're basically getting 1 choose 1, 1 choose 1, 1 choose 1, etc. For those 6 numbers. So it's 1 out of 49 choose 6. So 1 divided by 49. I don't know why I do this with my class because it's really depressing. I buy these tickets, but I always say, if I don't show up next week, that's why. So here, 7.15 times 10 to the negative 8. That's the probability that I will be a millionaire.
Just so you know, sometimes when you do zeros on the calculator and it says white equals, I get numbers.
Okay, so that's why it's not really a wise way to spend your money. But is that bigger than 0? Yeah. So it rounds to 0, but it is bigger than 0. I didn't have a ticket, I would never take it. So if I don't see you after the break, I wasn't at
Oh, that's why